October 29th, 2025. An interstellar visitor does something impossible. Hidden behind the sun's blinding glare, protected from Earth-based telescopes by 93 million miles of solar fire, the enigmatic object known as 3I Atlas reaches its closest approach to our star. And in that moment, as space-based instruments capture what ground observers cannot see, the comet does something that breaks every rule in the astronomical playbook. It turns blue. Not just any blue, but a shade more vivid, more intense than the surface of the sun itself. A colour that shouldn't exist on an object we expect to be freezing, dark, and covered in ancient dust. A colour that whispers of temperatures reaching nearly 6,000 degrees Kelvin, of energy sources that dwarf anything a natural comet should possess. This isn't just another data point in the growing file of 3I Atlas anomalies. This is the moment when the third interstellar visitor to our solar system stopped pretending to follow the rules and revealed something that has astronomers scrambling for explanations that don't exist in any textbook. The story of what happened on October 29th begins weeks earlier, when 3I Atlas started its final approach toward perihelion. Throughout September and early October, as the comet drew closer to the sun, it did what comets are supposed to do. It brightened. Solar radiation heated its surface, sublimating frozen volatiles, creating the characteristic glow and tail that define these cosmic wanderers. Observatories around the world tracked its progress, measuring its luminosity, analysing its spectrum, watching as it grew from a faint smudge requiring professional telescopes to an object approaching the threshold of amateur visibility. But by late September, Earth-based observers faced a problem written into the geometry of celestial mechanics. 3I Atlas was heading for solar conjunction. The comet's trajectory would carry it directly behind the sun from Earth's perspective, placing it in a zone where the sun's overwhelming brilliance makes observation impossible. From October 21st onward, when conjunction officially occurred, until mid-November when the comet would emerge on the other side, ground-based telescopes would be blind. The critical moment of perihelion, when the comet would experience maximum heating and stress, would happen in a blackout window that conventional astronomy simply couldn't penetrate. In any other era, this would have meant a frustrating gap in the observational record. Scientists would have tracked the comet up to the moment it vanished into the sun's glare, then waited weeks to see what emerged on the other side, piecing together what happened from before and after snapshots. But 2025 isn't any other era. We have eyes in space now. Multiple spacecraft positioned at various points in the solar system, equipped with specialized instruments designed specifically to study the sun's corona and the space immediately surrounding our star. And in a stroke of either cosmic coincidence or something more deliberate, 3I Atlas's trajectory placed it perfectly within the field of view of several of these space-based observers. The Solar Terrestrial Relations Observatory, known as STEREO, has been watching the sun since 2006. Two identical spacecraft, Stereo A and Stereo B, were launched to orbit the sun at slightly different speeds than Earth, giving us stereoscopic views of solar activity. Although Stereo B went silent in 2014, Stereo A remained operational, positioned ahead of Earth in its orbit. On its Secchi instrument suite, two cameras, HI-1 and COR-2, began tracking 3I Atlas as the comet entered the danger zone. The Solar and Heliospheric Observatory, SOHO, has occupied the first Lagrange point between Earth and Sun since 1995, a gravitationally stable position that allows continuous solar monitoring. Its LASCO C3 coronagraph, designed to block the sun's direct light and study the surrounding corona, provided another vantage point. GOES-19, a weather satellite launched in 2024 that normally watches Earth's atmosphere from geostationary orbit, carries the CCOR-1 coronagraph that can peer into the solar neighbourhood. And the newest addition to this fleet, the polarimeter to unify the corona and heliosphere mission, PUNCH for short, deployed 4 small satellites aimed at the sun, each one capable of capturing the faint structures in the interplanetary medium. These instruments don't see the sun the way our eyes do. Coronagraphs work by deliberately blocking the sun's disk with an occulting plate, revealing the much fainter corona and the space beyond. They're designed to study solar wind, coronal mass ejections, and the structure of the sun's outer atmosphere. They're not optimized for comet hunting. The objects they typically track are bright, explosive phenomena, not the subtle glow of distant icy bodies. But they could see through Eye Atlas, and what they saw rewrote everything we thought we understood about this object. Throughout September, as Through Eye Atlas closed to within 2 astronomical units of the Sun, then 1.5, the space-based observers recorded a transformation. The comet was brightening, yes, but not in the gentle, predictable way that standard cometry models suggested. Astronomers Qicheng Zhang from Lowell Observatory and Carl Battams from the US Naval Research Laboratory compiled the data from Stereo, SOHO and GOES 19, tracking the object's luminosity as it plunged sunward. What they found defied the standard inverse square relationship that governs how objects brighten as they approach a light source. The brightness of Through Eye Atlas was scaling inversely with distance from the Sun to the power of negative 7.5, give or take 1. That's not a typo. Not to the power of negative 2, which would represent simple reflected sunlight getting more intense. Not even to the power of negative 3 or 4, which might suggest some enhanced outgassing or unusual surface properties. Negative 7.5. This meant the comet was brightening approximately 100 times faster than it should as it closed the final gap to perihelion. Most comets discovered in modern surveys are faint at their best, requiring substantial telescopes to observe at all. Through Eye Atlas had been predicted to peak around magnitude 11 or 12 at perihelion, dim enough that only dedicated amateur astronomers with good equipment would have a chance of spotting it. The new data suggested something different. Based on the brightening rate observed by the spacecraft, Zhang and Battams calculated that at perihelion, Through Eye Atlas would reach approximately magnitude 9. Still not visible to the naked eye, but substantially brighter than expected. Bright enough that the comet might emerge from solar conjunction considerably more prominent than when it entered. This CCOR-1 instrument resolved details that added another layer to the mystery. Around the nucleus of Through Eye Atlas, extending outward for roughly 300,000 kilometers, was a glow. This wasn't surprising in itself. Comets develop comas, atmospheres of gas and dust sublimated from their surfaces that can extend for enormous distances. What made this glow remarkable was its scale and its composition. Previous observations by the Spherex Space Observatory in August had traced a massive plume of carbon dioxide around the comet, and the CCOR-1 measurements showed a comparable size. The comet was pumping out an enormous quantity of material, far more than its size alone would suggest. But the real shock came from the colour measurements. Earlier in its approach, Through Eye Atlas had appeared reddish in spectroscopic observations. This fit expectations perfectly. Comets are ancient objects, their surfaces darkened by eons of exposure to cosmic radiation, coated in complex organic molecules that absorb blue light and reflect red. When sunlight scatters off cometary dust, it picks up this reddish tint. Every comet we've ever studied shows this characteristic. It's as fundamental to cometary astronomy as ice melting in sunlight. Except now, in the LASCO and CCOR-1 colour photometry, Through Eye Atlas wasn't red anymore. It was blue. Distinctly, unmistakably blue. Not just slightly blue, not blue-tinged, but bluer than the Sun itself. To understand why this is extraordinary requires understanding what colour actually means in astronomical terms. The colour of an object tells us about its temperature and composition. The Sun appears yellowish-white to our eyes because its surface, the photosphere, radiates at approximately 5,800 degrees Kelvin. This temperature produces a specific spectrum of light, peaked in the yellow-green region, but including all visible wavelengths. Hotter objects appear bluer, cooler objects appear redder. This is basic thermal physics, the Planck blackbody curve, one of the most fundamental relationships in astrophysics. The surface of Through Eye Atlas, even at perihelion distance of 203 million kilometers from the Sun, receives about 770 watts of solar energy per square meter. That sounds like a lot, and it is, enough to vaporize water ice and drive vigorous outgassing. But it's not enough to heat a dark, rocky surface to anywhere near the temperature of the Sun. The nucleus of the comet should be perhaps a few hundred Kelvin at most, 20 times cooler than the solar photosphere, an object that temperature should glow deep red if it glows visibly at all. Adding dust makes things even redder as the scattered sunlight picks up the reddish tint from the particles. For 3 Atlas to appear bluer than the Sun means something is emitting light at temperatures approaching or exceeding 6,000 Kelvin, not reflecting sunlight, not scattering it, emitting it. The researchers noted that the shift to blue coloration combined with the rapid brightening suggested that gas emissions were contributing substantially to the object's overall brightness. Not dust reflecting light, but glowing gas radiating its own energy. This implies a massive release of power. When gases emit light, they do so because they're excited, energized by some process that pumps electrons into higher energy states. For hydrogen or helium, the characteristic emissions of the solar corona, this happens through extreme heating to millions of degrees. For other gases, it can happen through solar ultraviolet radiation, a process called fluorescence, which produces the characteristic green glow of comet comas as sunlight breaks apart molecules. But fluorescence alone doesn't explain a blue color brighter than the Sun. That requires thermal emission from something very hot, or an energy source we haven't identified. The timing of this transformation adds another dimension to the mystery. 3 Atlas reached perihelion at exactly 11:47 Universal Time on October 29, 2025. The uncertainty in this timing, based on orbital calculations from NASA's Jet Propulsion Laboratory, was only a few minutes. In that moment, at that precise distance of 1.36 astronomical units from the Sun, multiple instruments captured 134 stacked images from the Punch WFI-3 satellite alone, creating a composite that showed the comet in unprecedented detail. Not the nucleus itself, which remained too small and too embedded in its coma to resolve clearly, but the envelope of material surrounding it, now glowing with that impossible blue light. The geometry of perihelion passage matters for more than just observation. This is the moment when a comet experiences maximum stress. Solar radiation peaks. Tidal forces from the Sun's gravity become most intense. For spacecraft with engines, perihelion is the optimal time for major maneuvers, when a brief thrust can produce the maximum change in trajectory thanks to the Oberth effect. For a natural comet, perihelion is when fragmentation becomes most likely, when thermal stress and tidal forces can tear apart a loosely bound nucleus. If 3I Atlas were a rubble pile, a collection of smaller chunks held together by weak gravity and frozen ice, perihelion should have been its moment of truth. Instead, it turned blue and got brighter. Avi Loeb, the Harvard astrophysicist who has become the most prominent advocate for taking 3I Atlas seriously as a potential artificial object, immediately recognized the significance. In an essay published on Medium on October 30th, as the first data from the perihelion passage became available to researchers, he compiled the observations and added the blue color to what he called the 9th anomaly in the growing list of properties that make this object unlike anything we've seen before. The list Loeb has been maintaining reads like a prosecution's case file. First, the trajectory, aligned to within 5 degrees of the ecliptic plane, the disk containing the planets, with a statistical likelihood of only 0.2% for a random interstellar object. Second, the antitail observed in July and August, a structure pointing toward the Sun instead of away from it, something that can't be explained as a geometric illusion. Third, the mass, approximately 1 million times greater than the first interstellar visitor, Oumuamua, and roughly 1,000 times more massive than the second, 2I Borisov, while moving faster than both. Fourth, the arrival timing, fine-tuned to bring it within tens of millions of kilometers of Mars, Venus and Jupiter, while remaining unobservable from Earth during the critical perihelion passage. Fifth, the detection of nickel vapor without corresponding iron, a chemical signature consistent with industrial nickel, refining but essentially unknown in natural cometary emissions. Sixth, the composition of the coma, 95% carbon dioxide and only 5% water, the inverse of what every other comet shows. Seventh, the absence of a visible dust tail in high-resolution Hubble images despite clear evidence of outgassing, suggesting either an enormous nucleus or unusual surface properties that prevent normal dust production. Eighth, the non-gravitational acceleration detected by JPL engineer Davide Farnocchia, showing the comet experiencing forces beyond simple gravity, with a radial component pushing away from the Sun at 135 km per day squared and a transverse component of 60 km per day squared. And now ninth, the blue colour at perihelion, bluer than the Sun, impossibly hot for a natural object at that distance. Loeb has developed what he calls the Loeb scale, a ranking system from 0 to 10 that quantifies how likely an object is to be technological rather than natural, with 0 representing a definitely natural origin and 10 representing definitely artificial. Based on 8 anomalies before the perihelion blue colour was observed, he had ranked 3II Atlas at a 4. Following the latest data, in media interviews and public statements, he noted the ranking might need adjustment upward, possibly to a bit above 4. This might not sound dramatic, but in a field where most scientists reflexively assign natural explanations to everything, where even suggesting the possibility of artificial origins for an astronomical object invites professional ridicule, maintaining a ranking of 4 represents a significant statement. The mainstream astronomical community remains cautious, as it should be. Extraordinary claims require extraordinary evidence, and while the anomalies are real and documented, each individual anomaly has potential natural explanations. The trajectory might be coincidental, the anti-tail might be an unusual but natural jet. The large mass might simply mean we've been lucky enough to detect a genuinely large interstellar comet. The arrival timing might be selection bias. We notice and study the objects that pass close to planets. The nickel without iron might reflect exotic chemistry we don't yet understand. The carbon dioxide dominance might be characteristic of comets from other stellar systems. The lack of a dust tail might mean the surface is more cohesive than typical solar system comets. The non-gravitational acceleration might be normal outgassing producing a rocket effect, and the blue colour, well, that's where the natural explanations start requiring increasingly elaborate assumptions. Tom Statler, a NASA planetary scientist, maintains that 3I Atlas looks like a comet in just about every way. And in many respects he's right. It has a coma. It shows outgassing. It responds to solar heating. It's not a bare rock like Oumuamua appeared to be. But each time we look closer, each time we gather new data, the comet reveals another feature that pushes against the boundaries of what looking like a comet means. For 3I Atlas to appear bluer than the Sun through thermal emission would require temperatures approaching 6,000 Kelvin. No surface heated by solar radiation at perihelion distance achieves anything close to this. The alternative explanation, that we're seeing emission from highly energized gases rather than thermal radiation, requires explaining what's energizing those gases to such extreme states. Solar ultraviolet can cause fluorescence, but the resulting emission lines don't produce a blue continuum brighter than the Sun. Shock heating from high-velocity impacts of material might work, but what would be driving those impacts at such intensity? The possibility that draws the most attention and the most criticism is that 3I Atlas possesses an internal power source, something inside the object generating heat and light at levels that natural cometry processes can't explain. If outgassing alone were responsible for the brightness and colour changes, we should see corresponding changes in the spectrum, with specific emission lines from known molecules and atoms growing stronger. The data shows broad blue emission, more like a hot surface or plasma, than the characteristic spikes of fluorescent gases. Loeb has suggested the possibility of an engine, some form of propulsion system that could explain both the non-gravitational acceleration and the excess heat signature. This isn't as far-fetched as it might initially sound. We know that spacecraft approaching the Sun benefit from the Oberth effect, where engine burns at perihelion produce maximum trajectory changes. If 3I Atlas were designed for optimal navigation through solar systems, perihelion would be exactly when you'd expect to see enhanced activity. The blue glow could be exhaust, propellant heated to extreme temperatures, and expelled at high velocity, providing thrust while producing visible light. The energy requirements are staggering but not impossible. Earlier in the comet's approach, researchers estimated that if the observed accelerations were real and produced by directed thrust, the implied power output would need to be on the order of 10 gigawatts, equivalent to 10 large nuclear power plants. The brightness surge at perihelion, if it represents additional energy release rather than just more efficient conversion of solar input, could push this estimate even higher. But for a civilization capable of building an interstellar probe massive enough to survive millions of years of travel through the galaxy, a power source of this magnitude might not be unreasonable. The counter-argument is that we're pattern matching, seeing design where only coincidence exists. The universe is vast and old. Statistical improbabilities happen all the time. A 1 in 1,000 chance is just another Tuesday somewhere in a galaxy of hundreds of billions of stars. Maybe 3I Atlas really is a natural comet that happens to be unusual in multiple ways. Maybe interstellar comets from different stellar environments really do have different chemistry, different structure, different behavior than our solar system's comets. Maybe we're just revealing our ignorance about the full range of what comets can be. But the blue color is different. The other anomalies, taken individually, stretch, but don't break our understanding of natural processes. A blue color hotter than the sun, emerging from an object that should be 20 times colder, that's a direct physical impossibility unless something unusual is happening. Either our instruments are wrong, which seems unlikely given multiple independent measurements, or our assumptions about what this object is need serious revision. As October 29th became October 30th, and 3I Atlas completed its perihelion passage and began its long outbound journey, the astronomical community shifted focus to the next observational windows. The comet would remain behind the Sun from Earth's perspective for another 2 weeks, but other spacecraft could continue monitoring. ESA's Jupiter Icy Moons Explorer, JUICE, had a close encounter scheduled for November 4th, passing within 64 million kilometers of the comet. Its suite of instruments, including the Janus Visible Imager, the MAGIS Infrared Spectrometer, and the SWI Submillimeter Wave Instrument, would provide multi-wavelength observations as 3I Atlas began moving away from the Sun. By mid-November, the comet would emerge into the pre-dawn sky as seen from Earth, positioned low on the horizon before sunrise. Amateur astronomers with good telescopes, those with at least 8-inch apertures and dark skies, would have their first chance to observe the object since early October. Professional observatories would resume their monitoring campaigns. And most significantly, in December, when 3I Atlas makes its closest approach to Earth on the 19th at a distance of 267 million kilometers, the Hubble Space Telescope and James Webb Space Telescope are scheduled to conduct detailed observations. December's observation window will be critical. Hubble will perform ultraviolet spectroscopy, mapping the composition of the gas emissions with high precision, measuring the sulfur-to-oxygen ratio, and searching for unusual molecules. Webb will use its infrared capabilities to peer through any dust and directly measure thermal emission from the nucleus, constraining its size and temperature. Radio telescopes will listen for any electromagnetic signals, while radar systems might attempt to bounce signals off the nucleus to measure its shape and rotation. If 3I Atlas underwent significant mass loss at perihelion, as the non-gravitational acceleration data suggests might be happening, December's observations should reveal changes in the coma structure, brightness, and composition. If the object is fragmenting, breaking apart under thermal and tidal stress, we should see multiple distinct pieces where one nucleus used to be. If an internal engine or power source exists, it might still be producing detectable heat signatures even at the greater distance from the Sun. The most provocative possibility, the one that Loeb has repeatedly mentioned in interviews and essays, is that perihelion might have been a deployment point. If 3I Atlas is a mothership, a carrier designed to transport smaller probes through interstellar space, the close solar approach would be an optimal time to release those probes. The Sun's gravity could help modify their trajectories. The solar system's planets would be arrayed around the comet, accessible to vehicles capable of powered flight. Any mini-probes released at perihelion could reach Earth, Venus, Mars or Jupiter with relatively small trajectory corrections. This sounds like science fiction, and maybe it is. The history of astronomy includes numerous examples of mysterious phenomena that turned out to have prosaic explanations once we understood them better. Strange signals from pulsars that initially seemed like they might be artificial transmissions from alien civilizations turned out to be rotating neutron stars. Anomalies in the Pioneer spacecraft trajectories that some suggested might be violations of known physics turned out to be thermal radiation pressure from the spacecraft's own power sources. The unusual light curve of Tabby's star, which spawned speculation about alien megastructures, appears to be caused by dust from disintegrating comets. But the history of astronomy also includes examples of discoveries that genuinely did overturn previous understanding. Quasars were initially so puzzling that some astronomers seriously considered whether they might be artificial. Gamma-ray bursts had no good explanation for decades. The accelerating expansion of the universe contradicted everything cosmology predicted. Sometimes the universe actually is strange. Sometimes the data really does point to something new. 3i Atlas has now given us 9 documented anomalies, 9 ways in which it deviates from expected behaviour for a natural comet. Each anomaly has possible natural explanations, but the explanations become increasingly strained, increasingly dependent on multiple unlikely coincidences all happening to occur in the same object. At what point does the cumulative improbability of natural explanations exceed the improbability of an artificial origin? At what point do we take seriously the possibility that we're looking at something designed? The blue colour at perihelion might be that point. It's a direct measurement, not an inference. It's a physical impossibility for a passively heated object at that distance. Something produced that colour, that temperature, that emission spectrum. Whatever that something is, it represents physics we don't currently understand happening inside an object we can't fully explain. Over the coming months, as 3 Atlas continues its journey outward from the Sun, as spacecraft and telescopes collect more data, as researchers publish more papers and analysis, we'll learn more about what this object actually is. The observations in December will be particularly important, potentially decisive in distinguishing between natural and artificial hypotheses. The trajectory data will show whether the non-gravitational acceleration continues, whether it exhibits control and purpose, or fades as outgassing diminishes with distance from the Sun. Spectroscopic analysis will reveal whether the unusual chemical composition persists or normalizes. Imaging might show structural changes, evidence of fragmentation or deployment of secondary objects. Whatever the final verdict, October 29, 2025, represents a milestone in our relationship with the universe beyond our solar system. For a few hours, hidden from Earth behind the Sun's glare but visible to our spacecraft, an interstellar visitor did something unexpected. It glowed blue, brighter and hotter than it should, announcing its presence with a colour that challenges our understanding of what comets are and what they can be. And whether that glow came from exotic natural processes we've never seen before or from something deliberately engineered, it marked the moment when 3i Atlas stopped being just another astronomical curiosity and became a genuine mystery that demands explanation. The data is real. The observations are confirmed. The blue colour happened. Now we wait to see what 3i Atlas does next, and whether the answer to its mysteries lies in physics we've yet to discover, or in the possibility that we're not alone in paying attention to what crosses through our small corner of the galaxy. If you enjoyed this deep dive into one of astronomy's most fascinating current mysteries, consider subscribing to the channel. We'll be following 3i Atlas closely over the coming months as new data arrives and the picture becomes clearer. Hit the like button if you want to see more coverage of this story, and check out our previous videos on 3i Atlas, where we covered its discovery, its unusual trajectory, and the earlier anomalies that first caught astronomers' attention. The universe is full of surprises. Some of them might be natural, some of them might be something else entirely. Either way, we're living in remarkable times when the question of what visits our solar system has become something we can actually begin to answer with data rather than speculation. Thanks for watching.